Good morning, everyone. Good afternoon, good evening, wherever you are. Thank you for joining us. We've got the privilege of giving the first of the talks on array tomography today, which is a practical guide to starting SEM array tomography, very much with a focus on practical and starting. I want to say we, that's myself, Ian White, and my colleague Jemima who sat next to me. And I'm going to be taking you through the top row of this workflow from your resin block through to having your sections on substrate ready to go in the microscope. And Jemima is going to be taking you through the bottom row of this workflow, everything from your imaging through to having your beautifully aligned data stack, like we see this blood vessel at the bottom running through there.
所以这种 British 的口音，你听起来难受吗？不是很地道，我听不懂。
Now, Jemima and I work at the Laboratory for Molecular Cell Biology at University College London in the UK. And we work on the EM needs of everybody in our department and at UCL and beyond, in fact, on lots of different kinds of biological questions and lots of different model organisms. And until mid-2020, we were a TEM-only lab. We often did technically demanding correlative light and electron microscopy and 3D clem, which by definition involves serial section TEM. The problem with that is it has its limits. This is about as far as I'd want to go with serial section TEM, about 12 microns Z depth, and that's 168 sections spread across 7 of our TEM grids. Very technically demanding, very laborious, manually intensive. If you want to go further, as often our users do, they always want more, then you need a dedicated volume EM technique, and we adopted SEM array tomography. Now, the workflow begins here with your block, shrinking it down into a block face that's going to be suitable for sectioning.
I'm going to cut your hair. You're going to have to turn off the TV so I can have this running.
Then we have, in panel B here, we've got our sectioning and our forming of ribbons of sections that we're then going to have to break up into manageable chunks for collecting on our substrate, which we've got in C, and then mounting on a stub to go in the microscope here in D. And then Jemima is going to talk you through the bottom row from your low resolution, large area imaging of all the ribbons, through to your high resolution, low area imaging on all sections of the specific region of interest, which is going to give you your data stack to take away and analyze. Now, like all techniques, array tomography has its pros and cons. For a lot of people, they find it daunting. They think the real cons are that you physically have to collect your sections, and that can be challenging and they can be susceptible to loss. This was less daunting for us coming from a serial section TEM background, which is considerably more difficult. But what is true is that there is always potential for physical distortions when you collect sections, and there's going to be more alignment post-image acquisition than the other block face techniques. However, for us, this is massively outweighed by the advantages of array tomography, primarily that it's non-destructive, and that means that you can re-image as many times as you want. So that's the same area at different resolutions or different regions, or repeat imaging if something went wrong. You can image different regions of new interest that you've only noticed when you first go through your data stack that you've acquired. You can do multiple regions of interest, and not just one or two, but you can keep going back time and time again to image as much as you want. And right from the start, you have all of your Z information, and that can be quite important if you're looking for your region of interest, not just in X and Y, but in Z. It means you don't have to image everything at high resolution. It's also great for structures that meander, like blood vessels, which have been known to wander out of the field of view in the block phase techniques. And at any point, you can capture a large area context map as well as your high resolution imaging. So for us, this was the way to go. Now, I'm going to tell you about the sectioning aspect. And when you first start to look at this, you'll notice there's a bewildering array of options, if you'll excuse the pun. Starting off with how you prepare your block face, whether you use a diamond trimming knife or a razor blade, what shape you cut it to, what angle slopes, then what you're going to pick your sections up on, silicon wafer or what a glass cover slip or slide, or maybe tape. What kind of knife are you going to use? A fairly standard one or a jumbo knife, or a modified knife boat insert, or maybe the magnetized knife boat for use with magnetic resin. And finally, depending on how you're collecting, what kind of microtome you're going to use. With tape, are you going to have a RMC atom tone, or the Leica Artos 3D to help you out, or just go with your standard microtome? Well, we decided when we were first starting, and the best way to get started without a massive outlay at the beginning was to ignore the more expensive options and just to see what we could achieve with what we had to hand. And what we had to hand was razor blades, cover slips, and manual manipulators that we keep at the end of our arms, knives, so a standard knife and a jumbo knife, which we've made some in-house modifications to, and our Leica UC7 microtome. And we've found that for us, this has been sufficient to routinely and reliably get hundreds of sections collected. The longest we've done so far is about 700 sections, but we routinely do 500, 600s. And that makes this method accessible to everyone and highly cost effective. So let's start at the start. Trimming and forming your block face for sectioning. Your considerations are going to be that you want your block face to be fairly small, a little bit larger than the area you wish to image. The smaller it is, the more sections you're going to get on your substrate, and the fewer section breaks you're going to have to perform when you're making ribbons. You absolutely want your leading and trailing edges to be parallel. That's going to help you form ribbons, and that's going to keep your sections together and make imaging them in order much easier. And Jemima and I always like to introduce some asymmetry to our block face so that in our ribbons we can tell which is the start of the ribbon, which is the end. And again, that's going to help you in keeping everything in order for imaging later on. To form that block face, you can either use a diamond trimming knife, as demonstrated here. You can do one side with one side of the knife and then the other side with the other side, and those edges are going to be perfectly parallel. You can then turn this 90 degrees or just off 90 degrees if you wish to get your asymmetry in, and trim further with that. Jemima and I don't really have the patience for this though, so we like to attack our samples with a razor blade. And you can see this is a correlative sample of cells that were grown on a gridded cover slip. And this video is at 4 times real speed. And you can just see with the razor blade, we're trimming it down to just around the couple of cells of interest. And we're going to end up with a block face that is small, that has parallel leading and trailing edges, and is asymmetric. Is everything that we wanted. And this you can see from the time account took just under 3 minutes. So really it's not an overly long burden on your time. So you've trimmed down your block face and you're ready for sectioning. Before you start that, there's a few things you want to consider. How you can encourage your set ribbons to form, for your sections to stick together to stay in order. How you're going to split those ribbons to get them in manageable chunks for pickup on a finite size substrate. And then how you're going to organize those ribbons to get them all together so you can pick them up. Talking of substrate, you're going to have to think about what you're going to pick up on and perhaps any pre-treatments you're going to do to make life easier for yourself. And then we're going to show you 2 methods of section collection. One for shorter arrays and whereby we use a standard knife, and the second one for longer arrays, the 500, 600s, where we use a slightly modified jumbo knife. So first up, how do you ensure that you're going to get nice ribbons forming? Well, absolutely crucially, we have our leading and our trailing edges here that are parallel. And that's usually going to encourage your sections to come off in a ribbon that's going to stick together. However, it might not be quite robust enough for the amount of time it's going to spend floating around in a boat. So we like to encourage them to stick together a bit further by the use of some dilute contact cement on the leading edge of the block face. If you're in America, I think you can easily get hold of this kind of Weldwood contact cement that we dilute in xylene to make it more usable. And in Europe, we've got from Germany here this Patex gel, also diluted in xylene. I've used both. They're both equally effective. If you wish to know how to apply it, then the dilute glue with an eyelash, and you can apply a droplet, hopefully less clumsily than we're doing here. And you just drag that glue ever so slightly up to the leading edge. It doesn't matter if you're a little bit clumsy, as long as you don't get glue literally everywhere, you're probably going to be all right. I know Reza has a different method for ensuring you form sections, but I'm not going to go into that because I'm sure he's going to talk about that later. So now you've got your ribbon coming off your knife and it's forming these nice, long, robust ribbons that aren't spontaneously splitting apart. Nevertheless, you're going to have to break them at some point because they're going to need to fit on your substrate. And we feel there are 3 main ways that we've been able to achieve this. The first, you can just split on the fly. So whilst the microtome arm is in its retraction step, you just go in with your eyelash and just split the ribbon. Okay. Second, and Reza is probably going to talk about this further, we got this from him, from one of his talks. If you introduce a couple of cuts at very thin compared to your normal sectioning thickness, just there, and then you go back to your normal sectioning thickness, this induces a spontaneous break in your ribbon that we'll see here. And we'll see this ribbon break apart from that part that's still attached to the knife edge just about now. So this way you're achieving it without having to touch anything at all. Finally, you can stop your sectioning. Just detach the ribbon from the knife edge just by running an eyelash tool across the knife edge. Move that section ribbon away, back the microtome off a step, and just start cutting again. Now, all of these work. You'll have to have a play and decide which one works best for you and which one you like. But any which way you go about it, you'll be able to get your ribbons broken down into chunks that are small enough to fit on whichever substrate you choose. You then have to manage your ribbons in your boat and on collection. There might be different ways you wish to do this. Some people like to keep their ribbons split apart so they're not touching each other, and that can make life a bit easier for software sometimes in detecting each section. Or you can squish your ribbons next to each other. That gives a bit more stability when moving them around the boat, and also you can get more of them on the substrate. And you may wish to think about which order you're collecting your ribbons. So this one on the left goes from bottom to top, and then the next ribbon along goes from top to bottom. So this way, this might be section 54, and this might be section 55. And that way, when you're imaging in the microscope, there is less travel between the end of one ribbon and the start of the next, which is going to enable your auto functions to be more effective, to work a bit easier, and in the end, potentially give you better imaging. Whichever way you do it, your ribbons should be robust enough that we can steer them around the boat with our eyelash tools, and you'll notice the asymmetry in each section. That allows us to know which direction that ribbon's facing, so we can rotate it to get it in the direction we want. Squeeze it next to its chums here, so we've got all our ribbons all together, ready for collection.
Wow.
At this point, you may or may not wish to waft some chloroform over the top to stretch out some of the compression you may have got during sectioning. Some people like to, some people really don't. So your ribbons are all ready for collection. What are you going to collect them on? Well, we are now routinely using ITO-coated cover slips that we buy in. These are 22mm, but you can get other sizes. We have taken glass cover slips in our lab and carbon coated them, and we've used those with perfectly acceptable results. We just feel that the ITO coated is slightly more reliable, and it's not an expense that's really breaking the bank for us in this process. When you buy these in, it's worth noting they're only coated on one side. So you need to get a resistance meter and just check which side is coated and then mark it. So you're collecting your sections on the coated side. If you're only collecting small arrays, you might wish to break that cover slip up with a diamond scorer. But whichever way you do it, you're going to want to put some polyol lysine perhaps on your cover slip, either paint on some diluted stuff or dip it in some diluted polyol lysine. And we feel that helps your sections stick to the cover slip a bit better and lay down a bit flatter with fewer wrinkles. So you're ready to pick up your array. If it's a short array, probably 100 sections or fewer, you might want to do it on a fragment of cover slip. And for that, we can use our standard microtome, standard size knife, and our treated cover slip. And all we do is largely as we do for collecting sections on a TEM slot grid. The cover slip goes in, we manipulate the sections across to the water cover slip interface. And when they touch the glass, they tend to stick just enough that we can then lift that cover slip fragment out with the sections on it. We put those on the hot block until they're dried, and you can see there we have our fragments. This has got 100 or fewer probably sections on them. They're then ready to mount on stubs, either with copper tape or a carbon sticky, and go straight into the microscope at that stage, or store indeed for a later date. If you're picking up larger arrays, so our 500s and 600s, we use what we like to refer to as the PC method. That requires your standard microtome, but this time a jumbo knife, which we have modified in-house with a paperclip, hence the PC. Now, all we do with that paperclip is just straighten it out with a pair of pliers and then bend it to fit over the wall of the knife, run along the bottom of the trough and over the other wall, and we secure it in place with some high-tech sticky tape. And the function of this paperclip is to prop our cover slip up in exactly the right place so it's not going to move. So we have the back end of the cover slip resting against the back end of the knife boat and probably protruding from the water by about 1 millimeter or 2. Here's the water cover slip interface just here. We make two other modifications. One, we have a marker pen mark about 18 to 20 millimeters from the knife edge. And this acts as a visual cue to tell us that when our ribbon gets about this long, that's about the time we need to split it, because otherwise it's not going to fit on our substrate. And finally, we attach a syringe to some silicone tubing, and that attaches to the water withdrawal needle, which goes into the boat. And we can just use our left hand to withdraw the water, and that's what's going to get those sections to sit down on the cover slip. If we look at a video of that here, you see there's our sections we corralled earlier. We can move them down towards the back of the knife boat, over the paper clip you can just see here at the bottom of the water. And unfortunately, our camera doesn't go all the way back to the back of the boat, but when these sections make contact with the cover slip, they tend to stay in place ever so gently. And then we're ready to withdraw the water. So we keep our right hand on the eyelash just in case they try and escape. With our left hand, we withdraw the water, and you can see that happening, and those sections sitting down on the cover slip, which we can then withdraw and dry on the hot block again. It looks like this, usually looks like this, Occasionally they go a bit wobbly, but these are all perfectly acceptable to get you decent data off the microscope. And again, they can be mounted and stored for later or straight into the microscope. So just to summarize this section preparation part of the talk, we've been able, using no real specialist equipment and with no huge financial outlay, to get started in array tomography. And that's allowed us to reliably and quickly produce arrays of several hundred sections. And by quickly, I'm talking about an hour and a half from starting to attack your block with a razor blade to having your sample in the microscope. All achieved with just razor blade, some cover slips, our hands, knives that we had in the lab, which we performed slight modifications to, and a standard microtome. And having done all that, you're ready for your imaging. And that's where I'm now going to pass you across to Jemima to tell you about that part of the process.
Thank you, Ian. So the imaging is also relatively straightforward and logical, starting from mapping your ribbons, marking your sections, placing your regions of interest, setting up your imaging parameters, starting imaging, aligning and export. But as with everything with array tomography, because it's such a flexible technique, you also have options. And this can be not only the options and strategies that you choose to apply for each of these different steps, but also in the SEM hardware that you use, the detectors that you use, as well as the acquisition software that you use. And as far as I'm aware, currently there are about six different commercial manufacturers of EMs and array tomography solutions. These range from developed to just being released. And so you have plenty of choice. Now, we have a Xi system, so most of our experience is related to that. Having said that, the things that we have started to consider, we regularly consider within strategies for all of these steps, probably are helpful and useful for other manufacturer solutions as well. So firstly, mapping ribbons. So here the aim is literally just to mark a bounding box around where your sections are on the ITO coated cover slip, and then take a low resolution, say 600 nanometer pixels, to map out where all your sections and ribbons are. And here it's worth thinking about what area of your section do you actually need to image to find your region of interest, and what resolution actually do you need to image to be able to recognize your region of interest? Because it may be that you could work with this type of resolution, or it might be that you want to acquire a second image at higher resolution where you can maybe immediately see your features of interest. For marking sections, there are a variety of tools. For example, a stamp tool where you outline your section in the first section, and then you use a stamp literally to place this outline directly over the subsequent sections, adjusting it if needed as you go. And the software helps by moving the stage forward. Or, for example, a snap tool, where you do the same thing, you outline a section, but this time you don't have to quite so accurately place your section outline, and it will automatically snap the outline based on the image of your overview of your ribbons. Now again, here you might want to think it's quite useful to think about what you need to follow through your sample. And when I mention that, I will jump a little bit to some high school geometry. Because if we think back to our sample and our region of interest and how it meanders through this trapezoid shape, we also want to consider the geometry that will be affected as we section through it. So it's quite clear from simple trigonometry that your first section is not going to be the same size and potentially even the same shape as your, for example, 600th section. And this is where the beauty and the crystal ball feature of being able to see all of your sections in advance can be really helpful and allow you to map your feature of interest, even if it meanders in Z or in X and Y as you move through Z through your block. So one option is also, instead of mapping the outline of your section, is to use a slightly artificial section outline, centering it on your feature of interest, keeping the parallel parallel to the leading edge so that you can maintain rotation throughout your section set. This can be quite an easy, handy way of following your region of interest through your data. So now it comes to placing your region of interest. So again, the question, things to consider are, what do you actually need to image for this stack? And so you can pick your tool to outline your feature of interest, and you can check the position of this in all your subsequent sections by scanning through the sections. You can also modify this either for one region of interest for every section, or modify each outline for each section, or each and subsequent sections. This can be really handy, especially if, like this example for a brain lobe, which is essentially a sphere, if your feature of interest starts small and gets bigger as you go through into the block, this means that you don't have to necessarily capture gigabytes of bare empty resin, using up both imaging time and data size, as well as computational costs later on. And then setting up your parameters, and everything from pixel size, dwell time, field of view, and how you want to mosaic, as well as the auto functions, focus, stigmation, and location. And this will be based on your research question and the resolution that you need to see your features of interest. The field of view, you need to capture enough context to make your answer your question. And also where you want your auto functions to be formed, because you don't really want your auto functions to be performed on bare resin. And here there are numerous different ways that you can adapt and control this. And a lot of this is related, we've picked up various tips and tricks along the way, but this is mostly related to our software and perhaps less relevant to different manufacturers. And then you start your imaging. And the beauty here is you select your protocol, you select the sections you want to acquire. You can check that it's, even remotely from home, that it's doing the auto functions as expected and that the resulting images are in focus. And you can go off and sleep, have coffee, have a beer, head to the lab, check your email, not necessarily in that order. One thing we've also found is it's quite handy to have be able to align your data before you export it. This is because sometimes you collect more than you actually need to export, and this allows you to make sure that you export only the data that you want. We often do this in the in-house software, and then we also do it later, often using TrackEM and Fiji. And then exporting, what do you actually need in your data set? And here you can pick not only the resolution that you want to export it at, but the section range that you want to export it from, and the exact X, Y, and Z dimensions that you want to create your data sets to, as well as choosing the export format. And this can be very handy when you're working and collaborating with people all across the world who have different needs. So I'll quickly give you some examples of some of our in-house test data, whether it's TEM and SEM comparisons, sample preparation protocols, or different cover slips, and whistle stop through some project collaborations. So here is an example of TEM on the left versus SEM, and these both are at around 8 nanometer pixels. And if we just zoom into those images, just to give you a comparison. So for many features that you're, at least a lot of our researchers are interested in, it's easily enough resolution. And this is using our slightly modified Darrington Esmond prep on ITO cover slips. And then another example of mid-bodies from stem cells. And then here's an example of using, instead of ITO-coated cover slips, using carbon-coated cover slips, where we can easily still get decent imaging and see all the regions that we need to. This is now a TEM prep. So our routine TEM prep has a reduced osmium and tannic acid, and then these have been collected onto ITO cover slips and then lead citrated on the cover slip. And just an example of the types of resolution and images that we've been able to get. And similarly, testing immuno-friendly preparations, high pressure freezing, freeze substitution, etc., and low contrast, but with lead citrate on section. again on ITO coated cover slips. And then finally, just a few examples of different model systems, whether it's cells grown on cover slips, whole retina targeted for ommatidia, or correlative experiments targeting specific cells in the mouse hippocampus, or other correlative experiments, this time in liver, or following vasculature in the human sciatic nerve, or in Drosophila. Again, some of these are clone experiments. So what's some of the exciting futures? So I think there have already been numerous improvements along the way, and I think there are lots to come, whether this is improvements in long serial section collection, or more automated tools for sectioning, or more commercial solutions for imaging, better detectors, better acquisition softwares, both commercial and open source, better tools for analyzing, as well as a lot of this is being spearheaded by a really active community. And some of it who have got involved, if you want to get involved, is the EM community. So there's a volume EM community, and Martina's going to talk a little bit about the array tomography network and training group. And if you're interested in finding out more about array tomography as a collaboration between the two, we've got an array tomography focused interest group. You can either check out the website or the Slack channel. And that just leaves me to thank you for listening, and all of our collaborators. And if you want to find out more, there's a lot of volume EM amazing work on the 3D Light to EM science paper and linked videos, as well as the volume EM methods book. And I'd like to thank Wellcome Trust and UCL for funding, and Zeiss for not getting too annoyed when we have lots of questions. I think that's us.
Okay, any questions? We are opening for, we have time to take 1 or 2 questions.
I'll stop sharing. You can actually see.
Well, Jemima and Ian, thank you. Such a detailed introduction for us, especially for people who just want to start the array tomography. I have one kind of unrelated question. Are you a fee-for-service facility? How do you guys handle this type of really labor-intensive project when it comes in?
We are, but as Ian mentioned, in some ways, when you look at the whole workflow, you think how long it takes to get to the sample. Once you have a resin embedded sample, it is only a couple of hours before you have a cover slip of hundreds of sections. The imaging is very much, I guess, the same as everyone knows, that how long is a piece of string, because it completely depends on what you actually need to image, how many sections, what volume, what area, what resolution. But so far, it's okay.
I mean, it's worth mentioning that in terms of our staff time, then that initial setup, marking sections, picking region of interest, okay, that takes some time. But then a lot of the imaging is, as Jemima says, you set it going and then you're off doing other stuff, or you're off over the weekend, or you're off overnight, whichever. So a lot of that is microscope time where it's running away in the background.
Any
Yeah.
other questions?
Ruchin, can I ask a question?
Sure, sorry, I didn't. Yeah, go ahead.
So why do you prefer ITL's cover slip glass rather than silicone? Can you tell me about that? Because it seems to me the silicone is kind of grounding better than the glass or whatever.
I guess that's a little bit historic, because a lot of our original experiments we also want to do correlatively. So depending on our microscope setup, we also want to maybe do light imaging on the cover slips. So that was why we originally started there, because we wanted that to work. Yeah, so lots of people who use silicone and love it.
I like your modification of the large knife, of the histo knife. I really love it. You know, it's really a revolution. You know. So you also did it on the low crew embedded samples, right?
HM20, yes.
Yeah.
Okay, thank you. I may need to touch base with you about a couple of things.
That's fine. All good.
Okay.
Alice or Reza, you have a question or?
Yes, I do have a question. Great
Okay.
talk, Jemima. So I have a question regarding your sample prep. I think right now for the array tomography, you just routinely use tannic acid, don't use the OTO method as a TCH. So you think that that's better in terms of all the every structure preservation, or you know, for the contrast is enough for the array tomography?
We actually use both. So if we know it's definitely going to be for array tomography, we'll actually use a slightly modified Derink and Ellisman protocol. It's just slightly modified and it's a little bit less times for most things, a little, and maybe a couple of bit, nothing hugely dramatic. But we do have some projects that we want to keep the TEM prep because it does give a little bit finer details actually. But then you always have the risk of post staining, you always have the risk that lead citrate always has of maybe ending up with something where you don't want it.
I would say that using the heavy metal protocol, then what you're doing is you're usually, by doing that, cutting down your imaging time because you can image a bit faster because you've got so much more contrast in there. So it can make a difference over hundreds of sections at high resolution, quite a big difference in imaging time if you're getting your heavy metals into your sample en bloc.
Do you also need to coat with carbon after you staining, or you don't? No.
Not when collected on ITO coated cover slips, no.
Okay.
Did you do the imaging with the new detector from Zeiss that now they start marketing like the CBS detector, the detector that goes under the pole piece, or you imaging column detectors?
We use the sense detector, which is the new Zeiss detector.
Yeah. Okay.
We had the ABSD beforehand. That was perfectly
Okay.
The sense detector is faster though.
Yeah. Okay. Thanks.
So I wonder if you could comment on section thickness and how you would determine your preference.
Yes, I'm going to leave Ian to answer that actually, because he's done some testing recently.
So partly the preference of what you section thickness you cut at is dependent on your research question, how much your sample is going to change over that distance. When it comes to imaging, then I've played around with imaging conditions and I've imaged between 50 nanometers and 500 nanometer thick sections. And I've just had to, tweak a bit my landing energies just to change that kind of charging that you might get on the thicker sections, where again, you're more akin to like a block face when you get a very thick section there. So we've been able to successfully image any thickness section. So which one you choose is just dependent on your research question and what it is that you want to see and how much change you see over Z within your sample.
Thank you.
Ian, on carrying on for that, sorry, I've had to run in and out, so I may have missed this. Apologies if I have. What size sections have you cut successfully, as in the biggest? Not in Z, in X and Y.
In X and Y. So you can definitely go bigger. Okay, so I've looked at, so one of the projects I looked at on TEM was a mouse spinal cord. And I was having to divide the spinal cord and only do half of it because that's all that would fit on a 2x1 mil slot grid. I've cut sections of whole spinal cord and looked at them on the SEM, and that was great. So I've gone up to that size, so bigger than you can fit on a slot grid. Probably about
2 millimeters.
You're limited by potentially your knife width.
Okay.
I think Martina, I don't know if she's still here, but she has done some quite big things, so she might also be able to chip in either now.
I can also chip in. I'm Jenna, one of the speakers too. We've been working on whole mouse brain sections at the Allen Institute of sagittal sections, which are about 6.5 to 7 millimeters wide. So you need the 8 millimeter histo there. And then we can't get the full Y range is too long. But what we found is anything above 4 millimeters in your Y direction and 5 in your Z direction gives off chatter in the Leica microtomes. So that's where we've really started to struggle there. But smaller than that works pretty well for anything.
Yeah, I did wonder about, and obviously that'll depend as well on what exactly is sectioning. Yeah. But I did think about the compression and at what point. But wow, that's big.
Yeah, different resins are our friends right now in that. So I can chat later with you about that if you want.